So it seems like a few people wanted to see the most recent problem. That was number 28 in the textbook. So they start by giving you the equation for the frequency of vibrations of a violin string. And so it's given as F equals 1 over 2L times the square root of T over rho, where F is the frequency of the string, L is the length of the string, T is the tension in the string, and rho is the linear density of the string. So the problem's broken into two parts. They want you to find the rate of change of the frequency with respect to these three different quantities, with respect to the length, with respect to the tension, and with respect to the linear density. And then in part B, they want you to determine, based on those derivatives, if the pitch of the string is increasing or decreasing. So in part A, we'll look at part little I first, or little Roman numeral 1. So they want you to find the rate of change of the frequency with respect to the length. So that's df over dl. The only thing that changes in all three of these is basically which of these three quantities you're going to consider to be the independent variable and which ones you're going to be treating like constants. So in this first part, we're going to treat L like it's the independent variable, like it's X, and then we're going to treat tension and density like they're constants, okay? So in order to do that, it might be helpful to rewrite this a little bit, okay? So we can rewrite frequency as 1/2 L to the negative 1 power times square root of T over rho. And notice we're taking the derivative with respect to L. So in this case, we can treat this whole square root as a constant. We can treat the 1/2 as a constant, and we can just look at this L to the negative 1 power and treat it using the power rule. So the derivative is going to be, we bring that negative 1 down, and then we multiply it by the 1/2. We multiply it by that square root of T over rho. And then we have L to the negative 2 power. Okay, so we decrement the power like we always do with the power rule. We can clean this up a little bit, and we can rewrite this as negative 1/2 1 over 2 L squared times the square root of T over rho. Okay, so that would be one form of your final answer. If you even just left it as something like that, that would be fine too. There's a bunch of different ways to write this, but this is probably the neatest way. It's also probably the way that's most similar to the original format, which can be useful as well. So that would be your answer for A, Roman numeral 1. For Roman numeral 2, again, now we're doing the derivative with respect to tension. Okay, so df over dt. So we're going to treat L as a constant, and we're still going to treat rho as a constant, but now we're going to treat t as our independent variable. And so, again, for all of these, it can be kind of helpful to rewrite the equation based on what we're calling a constant and what we're not. So in this case, we have 1 over 2L square root of rho, and then we just break out this square root of t here, okay? So the reason I've rearranged it like this is everything here is a constant, okay? Because t is the only thing that's changing. These other variables are no longer changing. And here's the part of the equation where you have the variable. So this is where you're going to want to take the derivative of. Okay, you can also rewrite this as t to the 1/2 power, and that can be especially useful because what we're basically going to do is apply the power rule for this one as well. So we'll bring this 1/2 power down, okay, and then we're going to decrement the power here. So we'll have 1/2 times 1 over 2L square root of rho, okay, times t to the, now 1/2 minus 1 is going to be the negative 1/2, okay? And again, you could just leave it like this, although this is a little bit messy, so we can clean it up. And the way that we would probably want to clean that up is we can write 1/4 L, and we can write square root of rho t, like that. Okay, so notice, because we're going to put this underneath because we have it to the negative power, so this is really the same as 1 over t to the 1/2, or 1 over square root of t, and then we can multiply that into the same square root, so we have 2L square root of rho times t, and then we have this other 1/2 out here, so that becomes 1/4. Okay, so that's your answer to part Roman numeral 2. And then Roman numeral 3, again, very similar idea, although in this case now we just want df over d rho, okay? In some sense, df over dt is going to be the most practical in terms of what could actually be done to a string in real time. On a stringed instrument, you can pretty easily change the tension. However, I mean, changing the length of the string would require removing the string and replacing it, and likewise changing the linear density would require the same kind of thing. So you can change the tension in a very fluid manner, but you can't really change the length or the linear density in the same kind of fluid way for a string. But in any case, this is in some ways just theoretical. So df over d rho, this is going to equal, and then we take a look at our original equation, and in this case, rho is our variable. So we can do kind of a variation of this equation here, where we might want to write this as square root of t over 2L, and then times rho to the negative 1/2. Okay, so again, what we've done here is we've kind of grouped it by, here's our constants, and here's our variable. So again, it becomes a matter of just sort of applying the power rule. So we'll bring this negative 1/2 down, and then we'll subtract another 1/2, or another 1 rather. So we will have negative 1/2, and then square root of t over 2L. And then we have rho to the negative 3/2. Okay, and then if we want to, again, write this in kind of a neater way, we can have negative square root of t over 4L square root of rho cubed. And that would be that. So that's probably the most compact way of writing it. So that's part A. Part B is a little more of an application. So they ask you, based on the signs of these derivatives, if certain things happen to the string, what's going to happen to the frequency? So in part Little 1, they ask you when the effective length of the string is decreased by placing a finger on the string so that a shorter portion of the string vibrates. Okay, so in this case, we're shortening the string by fretting it effectively. So we want to know, if reducing the length of the string is going to increase the pitch or decrease the pitch, basically. So we can see from our first equation that dF over dL has a negative sign. Okay, so that means basically that as the length of the string increases, the frequency is going to decrease. Okay, and we can see that if we instead decrease the length, that the frequency is going to increase. So all we have to say for Roman numeral 1 is increase. Okay. Similar idea for Roman numeral 2. They ask you the tension is increased by turning a tuning peg. So we're going to look at dF dt. And we can kind of see as the tension increases, the rate at which the frequency changes is going to decrease, right? Because we have the tension in the denominator here. But the frequency itself, if we look at the original equation, as the tension goes up, the frequency also goes up. So the tension will also increase. You can kind of, if you've ever played, violin or guitar or other kind of stringed instrument, you've probably had the experience of tuning a new string, and when the string is pretty slack, as you turn the tuning peg, the frequency increases pretty quickly, but as the string gets more taut, you have to turn it more and more, and it becomes harder and harder to turn it more, increase the tension, and you get a correspondingly lower change in overall frequency. So that's nice when that can kind of reflect our real world experience. And then Roman numeral 3, little 3, when the linear density is increased by switching to another string. So in this case, we're going to want to look at what we got here in Roman numeral 3, part A. So we can see we have a negative sign on our dF over d rho. And we can see in our original equation for frequency as rho increases, okay, as rho increases, because the denominator here, the overall frequency is going to decrease. So we can just say down here, decrease. Okay, so you can refer to the equations. You can also, at least in this kind of situation, just think about it logically. If you shorten a string or you increase the tension on it, it's going to vibrate at a higher frequency. And if you make the string wider or thicker, it's going to vibrate at a lower frequency. So hopefully this makes this problem a little bit more clear. Let me know if you have any questions, and I'd be happy to do some other problems if you have questions on those too.